we're going to get started talking about teaching biostatistics using JMP. So I'm going to follow some PowerPoint slides up in this corner. I'll keep them kind of small until we get to tiny content when I might want to expand it. And I'll be using JMP on the rest of my screen. So we'll kind of keep track of where we're going. These PowerPoint slides will be available to you after the webinar. I will post them with the webinar at our webinar library, which is jmp.com/webinar. But some other resources that are really useful that you should know about, even if you decide to zone out for the rest of this webinar. If you go to our main jmp.com website, at the top of that website, this is really tiny, but there's a tab that's called Learn. And that's going to give you some really great resources if you're new to JMP or if you're teaching with JMP and you want to have some quick ways to help yourself or your students dive into JMP and learn things quickly, or even enroll in a free online statistics class. That's all available at this tab. And then jmp.com/learn, this URL takes you to probably our fastest, easiest get into JMP resource, which is these one-page guides or corresponding like 2-minute videos. So if you've got students that need to learn how to make a bar chart, you can send them to this website and they can learn very quickly how to make a bar chart. jmp.com/academic is our academic team landing page. And so that's another place to go if you want to browse other resources for teaching with JMP. And certainly if you'd like to get in touch with us at any point, email us anytime at academic@jmp.com. So I will get started with an example today that is built into the software, but I've simplified it just a little bit. So I'm calling it Diabetes Simple. If you wanted to follow along with this, you could go to the JMP Help menu and to Sample Data Library. And there you'll find about 500 sample data sets that you can use as examples in teaching or for homework assignments. One of these is called diabetes. And so that's the data set that I've simplified just slightly. So the data are the same, but I've just made it look a little bit simpler for us. So this is what we're going to follow, and we're going to explore some of these variables today. And we're going to be using this data set to explore things like what kind of graphics can we build? What kind of descriptive statistics could we look at, and confidence intervals and hypothesis tests. We'll also look at linear regression, at logistic regression, at looking at cross tabulations or contingency tables. We'll talk about odds ratios and relative risk. And at the end, I'm going to give you a 1-minute here's what you might do about survival analysis, and a 1-minute, here's what you might do with mixed models, just dip our toes into what else you can do in this context of health sciences or biological sciences, the types of things you might be interested in. So visualizing data is its own incredibly deep topic. So there's so many ways we could explore these data visually. And one nice resource for glancing at this is this link, which I already had open. So now I've got it open twice. This gallery of JMP graphs, this is just a nice, simple place to get an idea of the types of visualizations you might want to have your students make. So things like a simple distribution with these bars, or a box plot, an outlier box plot in this case. So we see that some of these values were outliers. Something like a scatter plot when you've got bivariate distributions, or one-way ANOVA, a way to plot the difference of means of groups. Tests of p-values, we'll see plots related to that. Mosaic plots for cross tabulations for a categorical versus a categorical variable. Ways of looking at logistic regression. So many types of plots that we could create. Neural networks, things that become very complex. We can do 3-dimensional graphs or surface plots. We can look at dendrograms and clustering. We can look at principal components plots and just a variety of things. So many things we could be plotting. What we're going to do today is focus on a couple of the common things we might want to create. If you did want more information on creating graphics, that learning library has a whole section on graphical displays and summaries. And we have a webinar that we've done a few versions of a webinar with visualization and graphics. So those are other places you could go as well. But let's start with just simple ways of describing data for probably more of an intro stats level. First, we might be interested in just tabulating data, just getting a table of averages. So for this example with this tabulation in the top corner, I've taken the genders. We've got gender 1 and 2. I've taken age groups, and you see we have the actual age here, so I have to create those age groups. And then I'm looking at the sample size and then the average of this Y variable, the BMI, the blood pressure, and the total cholesterol. So let's explore the data a little before we make that specific tabulation. And one way we might want to just explore data is using this distribution. So if we go to Analyze and Distribution, and we take some of these variables, let's start with just these things that are labeled Y. I'll just look at those, and let's only look at histograms right now. So I'm checking this extra little box down here. So I'm going to say OK. And what we see here is this Y variable is distributed from values a little bit above 0 to about 350. Then there's a version called Y binary and a version called Y ordinal. Binary just has low and high. Y ordinal has low, medium, and high. So let's explore how these are related to each other by clicking on one of these bins. So if I choose the Y binary low category, you can see that low for Y binary includes low and medium in the ordinal, and that's these values here, the lower end of this distribution. If I click on the high, we get the higher end of the distribution. So Y binary high and Y ordinal high are exactly the same. So you can see one of the great things about JMP right away is that everything is linked. So as I'm interacting with one graphic, it's highlighting the other graphics, that data in the other graphics. You can see it's also highlighting those corresponding rows in the data table. So right now, all of the low Y binary or Y ordinal low are highlighted in the actual data table. If I went back and explored this with some of the other variables, let's include all the extra statistical stuff. So now let's go back, now that we kind of understand this is a continuous measurement, this is a binary version of it with just low and high, and this is an ordinal with low, medium, and high. And you can see these colored icons on the side that indicate these different types. Continuous is this blue thing, nominal categories is this red thing, and ordinal ordered categories is this green thing. So we see those three different options. Just so you know, in this data set, this Y variable is explained here in the note. I'm going to hover my mouse, and it says that this data table gives us 10 baseline variables and 6 blood serum measurements for each of 10 baseline variables, including the 6 blood serum measurements for 442 diabetes patients, and that response Y is a quantitative measure of disease progression 1 year after baseline. So a high number on Y is a patient who had very severe disease progression of diabetes. So high is not good. We want lower scores here. Okay, so let's explore a little bit more with these data. If we look at distribution and choose maybe the continuous Y and age and gender and BMI and blood pressure and cholesterol, I'll click these in, and this time I won't choose histograms only. And now we see a lot more information, all this information about minimum, maximum, and the quantiles in between. So we see that the diabetes disease progression goes from 25 to 346 in our data set. We see the ages, 19 to 79. We see that there are 2 genders. Gender 1 is the males and gender 2 is the females. And we have a slightly imbalanced, but nearly half and half. We see the distribution of BMI is from 18 to 42.2, for blood pressure from 62 to 133, and then total cholesterol from 97 to 301 in our sample. Now, one of the first things you might teach students in an introductory biostatistics class is testing the mean of one of these variables. So we could do that here, maybe with total cholesterol. We can see that the calculated mean was almost 190, 189.14. So we could establish a test that we'd like to make. We'd like to test if the actual true total cholesterol scores in the population this sample came from, if that true mean maybe is 195. So in the sample, we got something pretty close to 190. Maybe I would like to test, is it possible that in the population, the true mean is 195? So I would go to the little red triangle next to total cholesterol. And here's where I get all these follow-up things I can do. And in this case, I want to test a mean. So it's a little overwhelming how many things you can do here, but if we look through them, you can see some of them are just display options. So I could, for example, make this look a little more like a traditional histogram in this horizontal layout. or I could test equivalence if I'm doing testing drugs against a current drug on the market. I could fit a distribution, lots of different types of distributions I could fit to these data and see which distribution fits best. Could look at a quantile plot. So many things we can do here. But again, I'm going to focus on test mean. And we're hypothesizing that is it possible that the true mean is 195? Now with students, we teach that there's a t-test and a z-test for a test of the mean. So this actually tells us right here what the trick is about these. If we know the true population standard deviation, then we'll be doing a z-test, and then we would enter that here. If we don't know it, then we're doing a t-test, and we leave this blank. And there's a corresponding non-parametric test, which is the Wilcoxon-signed rank test. So we could also ask for that if we'd like the non-parametric test. That's the test that doesn't assume normality of this distribution. Now, if we look at it, it looks approximately normally distributed, so I'm not worried, but we could do this non-parametric test instead. So when we do the test mean, we see this output that tells us, okay, the hypothesized value is 195. The actual estimate from the sample is 189.14. We had 442 people. We take away 1 degree of freedom for this test, and so we have 441 degrees of freedom. Here's the sample standard deviation that will be used for our t-test. And then here's that Wilcoxon-signed rank test. So we get a test statistic, and that test statistic is being compared to a null distribution, which is centered around the hypothesized value. So 195 is right here. The null distribution, the null sampling distribution is centered around that. And we see a little red mark showing us where our sample statistic, 189.14, falls compared to that null distribution. Then we see the p-value. We see the two-sided p-value. We see the upper p-value, and we see the lower p-value. So the two-sided p-value is tiny. So if we're doing a two-sided test, just saying, is the true mean not equal to, is it equal to 195 or not equal to 195, then our p-value is 0.0001, and we can reject that null hypothesis. If we hover our mouse over that 0.001, it tells us that p-value is small enough to indicate very convincing significance. P-values are the probability of getting an even more extreme statistic given the true value being tested is the hypothesized value, which a lot of times we test these against 0. Here we're testing it at 195. So we can also explore this a little bit deeper by looking at a p-value animation. And this lets us try some other things. So instead of a hypothesized mean of 195, so here's the null distribution centered around that 195, what if I hypothesize something larger? Then my p-value gets even smaller. What if I hypothesize something much closer to the sample value? Then my p-value gets really big and I fail to reject. Another thing we can do here is see, what if I had a smaller sample size, just 40 instead of 442? So I see how the distribution changes and how my t-ratio and p-value change. I can also choose to just look at the high side or just look at the low side of my statistic under the null distribution. So these animations can be really helpful for helping students really understand the meaning of these hypothesis tests. There is also a power animation to help you visualize what the power of the test is. Okay, I'm going to close this distribution output. There's obviously a lot more we can do here, but we're going to close this for now and try looking at a few other things. For example, making a table. So if we wanted to make a table like this tabulation that I've got up in this PowerPoint slide corner, I needed to create age group bins in order to make this particular table. So what I've got now is a distribution of age. Let's look at maybe the distribution just of age. And we'll turn it into that horizontal again. So I've got this distribution and I want to cut it into bins. I want to bin the age groups into categories. So maybe I want my ages to be from 15 to 25 years old and from 25 to 35 years old. That's what I did for that tabulation earlier, and that's what we'll do now. So to create something like this, if you're a JMP user, you might already know this, but if you are new to JMP, the way you do this in JMP is you select the column you want to act on, and then you get these columns options from the menu bar at the top. So from columns, I can go to utilities, and there is a built-in binning formula. So this is the fastest way I can think of to do this. It's pretty easy. There are many other ways in JMP that you could create this, but this is a really fast one. So this dropdown is just telling me how it's going to label the categories. This is telling me how I'm creating the bins, and it's showing me the different bins. So the offset is where it's going to start the first bin, and it starts it at just below the first value. I'm going to start at age 15. Our first patient was, our youngest patient is 19 years old. So I could start anywhere below 19. And then if I do them as a width of 10, that means it's going to do it from 15 to 25, 25 to 35, 35 to 45. And I come from a math background. And so the way I think about these is this mathematical way of writing those intervals that helps me remember which of these numbers is included in that group. So that square bracket by 65 says it includes 65, and the curvy bracket says it doesn't include that number. So this bin would be from including 75 up to just before 85. And then the next bin would be including 85 to just before 95 if we had data up there. So that's my favorite way to label these. So I'm going to use that and click this Make Formula column. So when I do that, I now have the age group categories. So let's look at a distribution of that. And I'll turn this one horizontal as well. If you find yourself doing the same change all the time, you can actually make these changes permanent in the JMP preferences. On Mac, it's under JMP preferences. On Windows, it's under File preferences. But in the preferences, you can actually ask it to do things all the time for you. So under the platforms, I'm in distribution. And I can ask it to always do the horizontal layout, for example. If I find that I'm always checking that option, I can just check it here and have that permanently be turned on. So here I am with my age groups, and I can see how it was binned. I can see that the lower group took those from 15 to 25, from 25 to 35, from 35 to 45, 45 to 55, and so on. So those are my age groups binned. So now let's make a table where we explore some of the other variables by gender and within those age groups. To do that, we go to Analyze and Tabulate. And in Tabulate, we just drag and drop things to make a table. So what I want here is to look at, let's look at maybe the Y and blood pressure and total cholesterol and glucose. Be these variables. I'm going to select them and drag them in as the columns. It started by giving me the sum. I don't want the sum, I want the mean instead. So I'll drag it on top and make these the mean. I think I can also ask for the sample size. And now I'm going to split this information out for some of my groupings. So if I group them by gender first, I have the two genders and how many are in each group, and then those means. And then if I want to also group them within the age groups, I can either prepend the age groups before gender. So I do the age group and then split it out by gender. Or I can take the age group and put it on the other side and have gender first, and then within the gender, have the age groups. So lots of flexibility on my table. If I don't like the number of decimal places, that's this format. I click Change Format. And so, for example, I can ask for all of these to have 1 decimal place, or however many. I can make it different for the different groups if I prefer that. But I'm asking for up to 10 digits with just 1 decimal place there. And so now there's not as many extra things after the decimal point. And when I'm happy with this, I click Done. I can save it out in a lot of ways. I can use this fat plus sign to highlight it and copy paste and drop it into a Word document or a PowerPoint slide. Or I can use this save script to data table as a way to save it back in my data table. I'll say okay. So now I can close it and it's saved in my data table as a thing I can repeat later. So let's do this for our distribution also. This is always an option at the bottom of the red triangle, save script to data table. And I can even do my other one here. Save script to data table. And I'll just keep using the names it's prompting me with. Now, if I save my data table and close it, when I open it back up, it has these 3 saved, what we call scripts. And when I repeat them, it just opens it right back up exactly like I had created it before. So this is a wonderful way for you and for your students to be keeping track of what you're working on. Okay, besides tables and simple distributions, we might also look at relationships between variables. For example, making scatter plots, maybe fitting a line to it, maybe looking at grouped distributions, maybe a logistic regression or a cross tabulation in a visual called a mosaic plot. For a lot of these visualizations, we might want to go to Graph Builder. So Graph and Graph Builder, this is super flexible. You can see we have other options as well. Bubble plots, if you've got a time element and you want to watch the bubbles move over time. Scatterplot 3D, this one's actually just a lot of fun because it allows you to see 3-dimensional things. So if I took, for example, our Y variable and BMI and blood pressure, we can see these in a scatter plot that we can rotate around. The dots are really small, so I right click and I look at the settings and I make those markers bigger. And that's a little easier to see. So then I can explore, oops, I just select some data, let's unselect it. So I can drag this around and explore where there's a lot of spread or where there's tightness. I can even do more things from the red triangle, like I could add normal contour ellipses. I could add ellipses based on the genders. So now I see the pink and the blue as 2 different groups, sort of where the data group for those 2 different, for the males versus the females. So really cool stuff we can do there, but most of what we're going to do for graphics is from this Graph Builder. So within Graph Builder, I might, for example, want to explore the relationship between maybe the response and maybe the LTG. We're going to use this for a regression later, so I could start looking at it as a scatter plot. So I have that diabetes disease progression as my Y and LTG as my X. All I did was drag them into those zones and drop them. I could split this out by gender in the 2 different panels if I wanted to, or not. I could put a best fit line. So you noticed it had a smoother to begin with. That smoother, we see more information about the smoother over here. We could make it really flat like a line, or really bumpy, really smoothed, depending on this lambda parameter. We can also add a confidence band around it. So this is really cool that you can actually get the 95% confidence band for a smoother, not just for the line of fit. So the line of fit also has a confidence band, and we can actually do the regression analysis right here by asking for the equation, maybe the R squared, maybe put the prediction band there as well. So there's lots of stuff you can do in Graph Builder, even analytical stuff, but it's also great for making these types of graphics. So if we have something continuous by continuous, we might make a scatter plot. Or if I start over, if we had something categorical by categorical, like if we look at the binary version of the response, the low and high versus the gender, and I choose one of these other options, I always am not sure between these 3 that look kind of similar. So this one's a heat map, this is a tree map, and that's the mosaic plot. So I click on the mosaic plot, and that shows me within each gender the proportion of high versus low. So this is a great plot, especially when you've got lots of categories. So let's switch out gender with age binned. Now we see within the youngest age category, they have lots of folks in the low diabetes disease progression. So younger people in our sample tended to have better diabetes disease progression. The older you get, the more your chance of being in that high group. So there's definitely an association here between age and that response. Okay, let's move into some analytics. So we've looked at some ways of describing our data with tabulations, looking at the distributions, even testing means, but let's do some more advanced analytics. And in this PowerPoint slides, I have a little note to you just to remind you to make that binned variable. You highlight the column you're interested in, for example, age. You go to that columns menu, utilities, and then that make binning formula. So that's in the slides if you need a reminder later on. We looked at testing a mean. So that was our first analytics, was just within distribution. We choose that red triangle. So we could look at maybe the total cholesterol. Also, we could test that. So if we look at the distribution of total cholesterol, we go to that red triangle, test mean, and we say what we're hypothesizing. So this was where we did, I think, 195 before, or we could choose something much closer, like 191. And now we have something that's non-significant on the two-sided or even on the one-sided. So now we see that we cannot say that the true mean is not 191 in the population. It's 189.14 in the sample, and it could be 191 in the population. We are not able to reject that from this test. Then moving into bivariate analyses, we're going to be using a tool called fit y by x. So in Analyze, we looked at distribution for those simple distributions and tests of one mean. We used Tabulate to make tables. We've been over here in Graph Builder to make graphics. Now we're going to use fit y by x. So fit y by x allows us to have one x variable and one y variable. In this case, we'll maybe use our actual y, our diabetes disease progression here, and we'll associate it with something. So I'm going to use this LTG variable. This is one of the laboratory measurements. And you notice it has this little grid at the bottom. I've put this grid in the slides a little bit larger. This is telling us that this fit y by x platform will actually do one of 4 different types of analyses. Whoops, I've moved this forward. Depending on the type of variables that you have. So I've chosen a continuous response, a continuous x. So I'm in this situation, continuous y, continuous x. So I'm going to be making a scatter plot and fitting a line to it. If instead of a continuous x, I had chosen something categorical, then I'd be in this situation here, which is like a one-way ANOVA. I keep accidentally clicking that. If I had chosen a categorical response, so maybe I use y binary as my response instead, with something continuous predicting it, that's called logistic regression, or categorical versus categorical is a chi-square test or contingency table or cross tabulation. So we'll get any of these 4 things from the same platform. Just go to Analyze, fit y by x, any of these 4 things. So let's start with this regression. And I've got a couple different regressions up here. So this one is fit of y by HDL. So we can see that there seems to be a negative relationship here. The higher your good cholesterol, the better your disease progression, the lower your disease progression. This LTG is the one I want to hone in on a little bit. And so this one is the serum concentration of this particular chemical in your blood. And this LTG relationship, we can get a line, and then we can look at tests of the intercept or of the slope of that line. So we use the red triangle to do anything. Fit mean would just fit a flat line at the mean, like it's saying when I hover. Fit line is what I'm looking for here. So this will fit a regression line. It tells me the equation of that line, and those parameter estimates are also down here. So this negative 235, this is the intercept, and this 83.5, this is the slope associated with LTG. And so specifically, we usually care about interpreting that slope. So our slope in this case of 83.5 tells us that every time we increase the x variable by 1, so for every 1 unit increase in LTG, we expect an increase of 83.5, that value, in the diabetes disease progression score on average. We expect this on average. It's not going to happen for every person, but that's the slope is telling us on average, that's the effect of every 1 unit increase in LTG. And usually when you report this in a paper, you would say what the p-value is in parentheses, and that's this little tiny p-value in orange, less than 0.0001. So that's typically what we're looking for from this type of relationship, is that slope for LTG and that p-value associated with it. We also often care about the r-squared. That tells us how much of y we can explain by x. So this tells us that our LTG explains 32% of the variation in y. So that's weak. It's not a very strong relationship, but there is a relationship there. So we see that significant slope telling us there's a non-zero relationship. And we also see this R squared is a weak R squared, but there is some relationship. We also usually want students to be checking the residuals. So there's another little red triangle there, and we have an option for plotting the residuals. The residual plots look pretty good. We're looking for sort of a random cloud. There's a little bit of increased variance the higher the Y predicted gets, but not a lot. This looks pretty reasonable. Okay, I'm going to pause here because we've covered a lot of content and we're about halfway through the hour to see if there's anything up to this point that you'd like to ask about. We're still going to look at ANOVA. We're still going to look at chi-squared contingency tables and mosaic plots. We're still going to look at logistic regression and odds ratios. We'll look at relative risk. There's still more content to cover, but up to this point, I'd like to know if there's anything I can help with or go back and repeat. So I'm going to pause for a moment, and if you'll write your questions in the chat or in the Q&A, then my colleague Chuck will be able to read your questions back to me and I can answer those.
Thanks, Ruth. Thus far, we have not had any questions, but as Ruth mentioned, please do feel free to type them in the chat or the Q&A section of Zoom. We'd be happy to answer questions as they arise at a good point.
I'll hang on just another minute or two. So if you do have a question, please type it. I'll give Chuck another chance to find those questions
Hey, Ruth, one did just come in. So, and this I think is more of a teaching thing, but how are you drawing on the shared screen?
What a great question. I think this is a really cool thing to do if you're a teacher, if you're trying to show JMP output, anything that is in JMP. So I can't do that on my PowerPoint slides, but anything in JMP, I have this little highlighter thing. That is a JMP tool in the preferences. So on Mac, the preferences is in JMP preferences. On Windows, it's file preferences. Once you're in that preferences in JMP, it's in, I believe, the general. Nope, that's not right. Reports? Yeah, it's in reports. In the middle here, this laser pointer, that's what I'm using. And when you first install JMP, the default is for it to be turned off. You can choose any of these colors for a laser pointer. Once that's turned on, then anything you've got open in JMP, you'll be able to do this. Another point about that, when you're trying to circle things, sometimes where you click matters. Like if I click right here, I can't get it. I have to click off of the plot. And then, I have to cancel this first. And then kind of zoom in. If I click in the plot, it has a different expected behavior. So once you get that turned on, then you'll learn the tricks of kind of starting out in the white space in order to get into something. Any other questions?
That's it right now. Thanks, Ruth.
Okay, great. We'll pause again in about 15 minutes to make sure that I'm keeping up with your questions as we're going through this content. I'm really covering an entire semester of statistics right now in this hour, so it's a lot of content, and if you've got questions, I'd love to be able to answer them. Okay, so we looked at fit y by x for regression and for interpreting a slope, checking residual plots, things like that. The next thing we can do with fit y by x is an ANOVA scenario. This ANOVA that we're going to do now is actually just two groups. When you've got an ANOVA with just two groups, it's really just a t-test. So t-test is also possible from fit y by x. You just need to have only two groups. So for the ANOVA, I'm going to use y as my response, the diabetes disease progression, and I'm going to use the gender now as my factor, and I'm going to test just on average, not worrying about all the other variables, just on average in my data set, does it look like males or females have higher diabetes disease progression scores? So when I say okay, the first thing I get is not a very attractive plot. It's just a stack of all those numbers corresponding to their diabetes disease progression for the gender 1, which was the males, and the gender 2, which is the females. And my eye can't tell which one is higher. This is not a very interesting plot so far. Sometimes when I'm trying to plot this, I find Graph Builder a little more helpful to give me a sense right away of the distribution. So if we were to explore this in Graph Builder, we would go to Graph and Graph Builder. We pull Y into this distribution, and we pull gender down here into X. And in this case, I pulled on box plots as well. And then I even colored them by their gender. So I created these plots, something like this. Yeah, and again, click done. Lots of ways to copy this out. One of them is to use this fat plus sign and Control C. You can also save script to data table. And something else that I didn't show you is you can also save this by going to File and Save As or Export. And you can save it as a PNG or an EPS or a lot of different file types that are higher quality than just a copy paste. So there's actually lots of ways to save this out. But again, I'm just trying to explore. So the box plots give me a better sense that it looks like the females might have slightly higher LTG because their mean seems to, or their median seems to be a little bit higher in the box plots. So let's test. Is there a mean difference between the genders? And then we can see which one is higher. When I go to that red triangle, I get all these drill down options. I see something that says means ANOVA pooled t, and I also see this t-test. The difference between these t-tests is this one's a pooled t-test, and this is a t-test with different variances for the two groups. So let's explore both, and let's even use this one. Let's first just use means and standard deviations. Means and standard deviations splits it into two groups, takes the mean and standard deviation within that group. We get confidence intervals for that mean within each group. So here we can see that the group 1, which is the males, has a smaller mean than group 2. So the males had an average diabetes disease progression score of 149. The 95% confidence interval on that is 139 to 159. And the females had about 6.5 higher points of 155.67. Their confidence interval on that from 145-ish to 166-ish. So it looks like maybe there's going to be a mean difference, but we should do the test. So that's when we have two test options. First, I'll do the pooled test. The pooled test assumes that those standard deviations between the two groups, let me try to smush this so it's easier to scroll. So that means and standard deviations, these two standard deviations here. Do we think that they're similar enough to be equal? They are pretty close, 76 and 78. So it's probably reasonable to use a pooled estimate of the error variance. When we do that, we get the same means for the two groups, but we get different standard errors of the mean here than we did here, because we're using a pooled common variance instead of just the separate group variances. Again, we get lower and upper confidence intervals for the two groups based on the pooled test. And here's where the actual pooled t-test results are. It's doing group 2 minus group 1, so females minus males. So this is a positive difference, which means females were bigger. Females have the higher value because females minus males, and it's positive. So females had a 6.6 points higher average difference. The two-sided p-value here is 0.3664, and here's our picture. And so this is actually telling us, even though it's a kind of big difference of 6 units, it turns out that compared to the variance of like a standard deviation of 75 or the standard error of 5, compared to that variance, it's not a big enough difference. So nope, it looked like maybe we had a difference, but it's not big enough to say that it's statistically significant. So our pooled t-test fails to reject the null hypothesis. And if we were to hover over any of these values, we should see those hover help pieces as well. We can do this one more way with this regular t-test for unpooled variance, but we get a very similar result. In fact, the p-value is almost identical. So assuming unequal variances, we still get a very similar result. So what we decide is that for the response, for the diabetes disease progression, we have no significant difference. But if we did this analysis for the LTG by gender, we will find a significant difference. So let's look at that one. So fit Y by X, we choose now the LTG as the response, and we split that out by gender. Still, I can't tell from the picture which one is higher. It's really difficult to see, but let's do the pooled t-test. And the pooled t-test now has a p-value of 0.0016 for the two-sided p-value, which is highly significant. And the difference is positive, so that means the females have the higher value. So females have an LTG on average about 1.5 or about 0.15 units higher than males. So our interpretation is that the females, group 2, have this LTG, serum concentration of lamotrigine, that is 0.15 higher on average compared to the males, and that two-sided p-value is 0.0016. Okay, some other things that we can do when we're looking at results like this. Sometimes the results automatically print these lower and upper 95% confidence intervals. Sometimes the results don't. So when we looked at the y by x with continuous versus continuous, we had LTG here. So this regression, and we fit a line. For this, we did not by default get those confidence intervals, the lower 95% and upper 95% on the slope, for example. So sometimes there are hidden things that don't come as the default in JMP, but you can still find them. Parts of the ways you find things in JMP are the red triangles. Red triangles give you lots of hidden things. Another way you find things in JMP is right-clicking. Right-clicking lets you do things in graphs like change the marker size or transparency or background color. There's lots of things you can find by right-clicking or by the red triangles. This is a right-click situation. If you want to see if you can get confidence intervals or more information about something, then you go to the table where it's reported. So like I want the confidence interval for the slope of LTG. I hover over the names of the columns, any of the column names. I hover over and I right-click, and it gives me an option to put more stuff in the columns. So let's put the lower 95% and let's put the upper 95%. Another JMP tip is if you want to select multiple things at the same time, you choose your control or option button first, then you right-click. So if you choose the control or option button before right-clicking, that should give you the chance to select multiple things. So let's try that here. Now I hover and right-click. I go to columns and I had the wrong button. So I just added standardized betas. So here I could report the LTG where the estimate for the slope is 83.5. So I'm saying that every 1 unit increase in LTG should result in an 83.5 point increase in diabetes disease progression. So LTG is a very bad thing for diabetes disease progression, but that 95% confidence interval is actually between 72 and 95. So I could also report the confidence interval. Okay, so that JMP tip is repeated here for you in the slides, and that's something that can just make you able to do a little bit more in JMP than just what the defaults show. All right, we've got 2 more big topics, and that's logistic regression and looking at odds ratios within logistic regression, and then chi-squared cross-tabulation contingency table sort of things with categorical versus categorical and looking at relative risks. So for logistic regression, same place, we're going for all of these things as analyze fit y by x. But the logistic regression context is where we have a binary response and then something continuous to predict. So let's use that LTG, which seems pretty associated, and predict just low or high. So remember our LTG, or our diabetes disease progression binary is just low versus high. And if I double click in here, it actually tells me where the split is. The high are everything above 200 and low is everything less than or equal to 200. So here I'm fitting this logistic regression that's showing me as I increase LTG, for the lower LTGs, I have a really good chance of being in the low group. The higher I get on LTG, the higher my probability of being in the high group. That's what this sigmoidal curve is doing, is it's the high is the top, the low is the bottom. So below the curve is the probability of low, above the curve is the probability of high. So I'm seeing that as I increase LTG, my chance of being low gets smaller and smaller and smaller and smaller. And that is a statistically significant, that LTG slope estimate now for the regression is highly statistically significant. And we probably would rather look at this as odds ratios. So we use the red triangle and select the odds ratios. And now we see the parameter estimate for LTG in terms of the odds ratio. So we have a unit odds ratio and just an odds ratio. This is actually called a range odds ratio in another platform in JMP. So unit or range. Let's talk about the unit odds ratio first. And it's actually easier. So I've got this little tip in the slides, whoops, at the bottom. It's actually easier to understand odds ratios if you can make them above 1. So this one being below 1 is a little bit trickier to interpret than if it was above 1. And this odds ratio is for the log odds of low compared to high. So it's low versus high. If I reciprocate this, if I do 1 divided by the odds ratio, then I can flip the direction of the log odds. So right now, this 0.065 odds ratio is telling me low compared to high. If I do 1 divided by this, then I have high compared to low. So that's what I'm going to interpret here. I'm going to do 1 divided by 0.065, and that gives us 15.37. And now my interpretation is for every 1 unit increase in the LTG, the odds ratio of having a high diabetes disease progression, so I'm interpreting high instead of low because I switched the order, compared with the same person without the increase of that 1 unit, is 15.37. So the odds ratio for someone, as you increase LTG by 1 unit, the odds ratio is 15.37. That's still a little hard to understand. So this means that if a person had an LTG of 5, that person would have 15.3 times, they'd be 15.3 times as likely to have a high diabetes disease progression score as they would have had if they had an LTG of 4. So same person, everything else held constant. If you increase their LTG to 5, they're now increasing their odds or their chance of getting this disease. They have 15.37 times as likely. Now, 15.37 times as likely is the same as 14.37 times more likely. So I put that in this second slide because a lot of students really struggle with this as likely, more likely, less likely. When you've got this odds ratio of 15.38, that's 15.38 times as likely to have a high score versus a low score, or it's 15.38 minus 1 more likely. And then, of course, the opposite of that, if we had interpreted the original odds ratio of 0.065 instead of doing the reciprocal, our interpretation would have been for every 1 unit increase in LTG, the odds ratio of having a low, we'd interpret low instead of high diabetes disease progression score compared to the same person without that 1 unit increase would be 0.065. And that means that a person with LTG equals 5 is 0.065 times as likely to have a low diabetes disease progression score as they would be if they had an LTG of 4. So it's a little bit easier to understand the things that are greater than 1, which is why a lot of times we'll do that reciprocal. Okay, last big topic is the fourth and final quadrant from our fit y by x. So if we go into fit y by x, oh, nope, we don't want to do that. I didn't tell you about the range odds ratios yet. So the range odds ratio is this guy here. And that's instead of interpreting for every 1 unit increase, this is over the entire range of your x variable. So now, if you have the highest value of LTG, so we're talking about the range of LTG in the whole sample. So the highest LTG in our sample, let's go back to this data table, analyze distribution and LTG. So the maximum LTG was 6.107. The minimum was 3.25. So that range odds ratio is telling you how much you change your odds of having high or low disease progression when you go from 3.25 to 6.107. So having the highest value of LTG in our sample, the LTG of 6.107, the odds ratio of having high diabetes disease progression score is 1 over that range score. So I'm again doing the 1 over and interpreting high instead of low. So I'm flipping this and I'm flipping this. So 1 over that 0.0000416, that's 2,403. So what we're really saying here is having the highest value of the LTG makes you 2,403 times as likely to have high diabetes disease progression compared to the same person if they had the lowest value of LTG, which was, so highest LTG was 6.107, lowest LTG was 3.258. So the difference in odds at the high end of the LTG range compared to the low end of the LTG range is that at the high end, you are 2,403 times as likely to have a high diabetes disease progression score. So LTG is, if it gets high, it's a terrible thing for your diabetes disease progression. So very associated with a bad outcome for your diabetes disease progression. Okay, last one, the contingency table, Mosaic plot, and looking at relative risks. So we can make a contingency table or Mosaic plot with as many categories as we want, but the relative risks are going to make the most sense in the 2x2 example. So we're going to look at fit y by x, where we're predicting the y binary by gender. So this is 2 categories versus 2 categories. Again, we can put in things with more categories, but this relative risk will make more sense here. So what we see is within gender 1, the males, that there's a longer red bar than blue bar. So there's more low diabetes disease progression within the males than there is high. There's less low than there is high compared to the males for the females, but still everybody's more likely to be low than they are high. If I right click, I can go to cell labeling and ask for things like the count or the percent. I put the percents over here, but we could also do it by the count. So there's 177 plus 58 males. There's 144 plus 63 females, and we can see how they're split into high versus low. We also see the contingency table that gives the total percents, column percents, row percents. We can ask for expected counts and chi-square counts and so on. And we see the likelihood ratio tests here, these chi-square tests. P-values are non-significant. So even though there's a bit of a difference, they're not perfectly distributed across those groups. It's not a big enough difference to actually be statistically significant. So we can ask for relative risk, and you can ask for which category you care about or just all of the combinations. So I'll do all of the combinations, and then let's look at that output. So we get 4 combinations. We get what is the relative risk of if you, so group 1, this group here, group 1, that's the males. So this first probability is the probability of a low diabetes disease score if you were male, compared to the probability of a low diabetes disease score if you were female. So let's interpret specifically this one at the bottom. So this one here is saying this is your chance of having a high progression score. So this is the thing we're kind of interested in. We want to be able to predict who is at the most risk of being high on this diabetes score. So the probability of being high if you're female compared to the probability of being high if you're male is 1.2. So this is like the odds ratio in that what we're saying, we see in the probabilities here, the probability of having a high diabetes disease progression score for females is 30.4. The probability for males is 24.7. And then if we take the ratio of that, 30.4 over 24.7, that's how we get this number, 1.23. So females are 1.23 times as likely to have a high score as males, which is the same as saying they're 123% as likely to have a high score, which is the same as saying they're 23% more likely to have a high score. But even though we find that females are 23% more likely than males to have a high score, This increase, this change between the two genders is not statistically significant, so we don't have evidence to believe that the males and females have a difference in the actual population in their percentage of having high scores. Okay, so we covered an awful lot of content there. I did want to mention quickly that there are platforms, ways to do different types of survival analysis in JMP. You would go to Analyze, and then there's a reliability and survival option. So under Analyze, reliability and survival, down here are the survival methods. So simple survival models, they don't include other variables. You can only group by something. Can't put other stuff in the model. Parametric survival is going to let you fit different distributions, and then an entire model and proportional hazards is a semi-parametric model that doesn't fit a specific distribution but still lets you fit a broad model. So this type of things, this Kaplan-Meier curve, is what you'll get from a simple survival analysis. Proportional hazards, you'll be looking at risk ratios, and the parametric survival, you'll be fitting different distributions and then looking at risk ratios. So if you are teaching and you need an example for this, that in that sample data in JMP help sample data library, the VA lung cancer data is a really nice example for survival. So if you do need an example, that's a good one. And then mixed models, another much more advanced topic, but very common in the health and life sciences. If you've got something where you're blocking, or if you've got repeatedly taking measurements over time, you're going to want mixed models. So there's a nice machine example if you just want to show what happens when you're blocking. So for example, if you want to take measurements of how well a machine performs and you care about those specific machines, you're going to always use those machines. But you have different people doing the rating, and every time you do this experiment, you'll get different people to do the rating. So you don't care about the person, then your person is what's called a random effect, and you'd put that in the model that way. Also, if you've got repeated measures where you're following people over time, this is cholesterol over time. This is a really good sample data set if you did want to show repeated measures models. So we've reached the end of the hour. I'm going to stay on for a few minutes for any other questions, but if you've got questions and you don't have time to stay on with us right now, you are welcome to send your questions to academic@jmp.com. But I'm going to open it up now for anybody who's got questions. Feel free to stay on and I'll answer questions.
Great, thanks, Ruth. We did have one or two questions come in, and again, if you have any more, feel free to post them in the chat or Q&A window. The first question had to do with sharing results. So specifically, how can students share or return their results from exercises?
There are many ways they could. If you are asking them to fill out a Word document where you are asking questions, they can be copying and pasting their results. So if, for example, we run let's see what my last model was. This is that cross tabulation. So if this is the output you wanted to see, the student could go to File, and on Mac it would be Export, on Windows it would be Save As, but I could go to Export and save this as an image, or I could save the text, or I could save it right into PowerPoint slides. If I do it as PowerPoint slides, I'm gonna let this open. This is what I get in PowerPoint slides. So the student is ready to wow the class with their PowerPoint slides just by dropping in all the elements. Or they can save it as an image and put it into a document. Or you can even have them create things and save that to the data table. So save script to data table, and then send you their data table. So that's yet another way that you could ask them to show you what they really did in the software. So many ways, but the simplest is typically you would be creating a paper document that would turn in for homework. And to do that, you can just save out with that File Export or File Save As. You can save any of the elements, or you can copy paste with this fat plus sign. So here I would Control C, and then let me open Word. And I'll Control V, and there's my Mosaic plot. So now I can write text around it and answer my homework questions and then submit the document. So I hope that gave you some ideas of how you would be saving output out of JMP.
Great, thanks, Ruth. Couple more questions. How do we sort from smallest to largest? Sort by category? as well as sort alphabetically in the columns?
Great question. So when I created that age groups bind, it already has an order associated with it. When I double click on it, it's got this, the value labels are already arranged numerically. But let's look at something like Y ordinal. That one had 3 orders to it. Typically, I'm going to edit some things here. We're going to get rid of the formula. We're going to get rid of the value ordering, and we're going to get rid of the sort ordering. So right now, this is just a typical categorical variable with 3 levels in it. And low, medium, and high, if I were to plot this right now in Graph Builder, something with the ordinal groups, it would, let me say, okay, let me try that again. I'm expecting it to do it alphabetically, so let me check. Still not. It seems to be retaining that, that column property. But what we would do is when you want to put things in a certain order, you go to the column properties for that column. So you click on the column, double click on the column, and then this column properties, there is something called value ordering. This lets you take the 3 categories and put them in the order that you want them to be. By default, JMP will use alphanumeric. So it will already do what it thinks is obvious, but if you want something different, then you can put them in a custom order. So if I wanted high always to come first, I move it up. If I wanted it to go high, low, medium, that's really bizarre, but I could do that. So I can apply that and say, okay. And now when I go to Graph Builder and I put Y ordinal down here, high comes first, then low, then medium. So I just made it weird, but you have control over what order you want them to be in. It's that column property. You just double click the column and you put this, you choose a column property, the one called value ordering.
And what about sorting within the column? Just an additional question there.
If you wanted to sort the data table within the column, so like if I wanted to stack the data so that the top bunch of rows were the low group, then the next ones were the medium, and the next ones were the high, that would be a table function where I'd go to tables, sort. I would be sorting the whole table by that ordinal variable. This tells me which order to sort them in, whether it's ascending or descending. And then I guess I'll replace the table. Let's make a new table. I'll call it new table. And I'll say okay. And so now I have the same table, but now it's sorted in the order that I told it that I like my ordinal to be sorted, where it does high and then low and then medium, because that's the order I've told it I like. So that's how you would sort the entire table, is table sort. If that's not the question you're asking, let me know in the and Chuck can redirect me.
Okay, so within this, do you have to enter gender by 1, 2? Why can't you just have categories of male, female?
Yeah, great question. You absolutely can code this any way you want. If I would prefer to have this say male, female, which would make sense, that I ought to do that. One thing I can do is go to the double click gender and put a label property. I can put value labels, and for 1, I will call these male, and for 2, I will call these female. I'll apply, say okay, and now what you see are the labels. Technically, it's still in the background, has the 1s and 2s, but you see the labels. Another way to change this is to take those value labels off. So now we're back to the 1 and 2. And now I could recode the 1. So the value label is actually labeling it, but not changing the 1 and 2 that's in the background. If I want to totally change the 1 and 2 completely to males, females, I go to columns, recode, and the gender 1 was male, and the gender 2, yeah, I'm turning I had numbers, I'm turning into characters. Yes, I do want to make that conversion. And the 2 was female. And I can recode in the same column in place, or I can make a new column, or even a formula column. Let's do that. click recode. Now it made a new column where it put those new, not just labels, it actually just changed them, it recoded them. And actually in the background, I have a formula that if I added new data, like if I, let's add a new row and let's have that person be female. So I'll enter a 2 here. Oops. When I enter the 2, it automatically recodes it as a female. So that's what adding a formula does, is anytime you add new information, it'll keep recoding it for you.
Awesome, thanks. Another question had to do with importing data. So can you show how to import from Excel and or a CSV file?
Yes, it's really easy. You go to File, Open. You point to your Excel or CSV file, and then you just click Open, and it will bring it in automatically. You can do this with 35 or 37 different file types. So most types of data files, you'll be able to just go to File, Open, and open it directly.
Perfect. Sort of jumping around here, back to the female example. Was there any sort of an advantage to using the 1s and 2s?
No.
It was just the way the data came in, correct?
Just the way the data came in. Yeah. I think in the past, it used to be easier because of typing and how we collected data, and there'd usually be like a data dictionary that you would have at the side. That's no longer an issue. So I'm unaware of any reason you would need to do that. JMP will do, anytime there needs to be some kind of indicator coding or hot one coding, JMP will do that internally. So it really doesn't matter how you label things. 1, 2, 0, 1, male, female, any of that is equally good.
Okay, and then a functionality question, how do you right-click on an Apple computer?
You have to set up your right-click. So you might want to Google this one, how to right-click on an Apple. I don't remember how to set it up. It's in your settings. For me, I set it up so that I have I put 2 fingers in the middle of my, the button part of the trackpad, and then I just press down, and that's my right click, but you set that up in on your Mac. But it does need to be a true right click, so you have to actually set up what your actual right click is. Yeah. So sorry, I didn't really answer that, but you can find that by Googling how to set up right click on Mac.
Great, Ruth, we appreciate it. I think we've worked our way through all the questions. If I happen to miss one, again, there was an email address Ruth provided, is academic@jmp.com. We do monitor that. We have staff who monitors that daily, so we hope to get back to you pretty quickly. Other than that, I think that's all the questions. Thanks a lot, Ruth.
Yeah,
and positive comments.
For attending. Yeah.
All right, and thanks to everybody for attending. Please do visit our website. We have many academic webinars scheduled throughout the semester.